So, Michele is going to talk about is monitoring nutrients helping us manage cyanobacterial blooms.
Yes. It's actually been a topic dear to my heart for many years, and I've had this fantasy about writing a paper or a technical report or something about it for a long time, and I thought this workshop was a perfect opportunity to force me to actually start to collate my thoughts on it. Okay, and I want to start by acknowledging the many staff and students who've contributed to this work. I've been working on nutrients for many years in marine and freshwater, cyanobacteria and other types of algae, and that's obviously been the work of a whole range of people and included funding sources like ARC and collaborations with a whole range of other researchers as well as water authorities. All right, so I guess I'm trying to be a little bit contentious here in terms of talking about nutrients, about do we need to measure nutrients? Do they really matter? And I guess in today's talk, I want to highlight some of the things I've learnt over the years about the challenges of measuring nutrients. Maybe we're over-measuring nutrients and not really using the data or don't understand what we should do with the data, and whether there's some different approaches that we can use. Obviously, nutrients have a place. I mean, it's well established throughout the world that many algal blooms are caused by higher nutrient loads, often anthropogenic loads. And so, you know, I'm not advocating that nutrients aren't important in terms of causing cyanobacterial and other blooms around the world. But if it was that simple, we would just be able to measure the amount of nutrients and we'd know what kind of bloom, what scale of the bloom, and the magnitude, the duration, and the frequency of the bloom. But it's not quite that simple. We also measure nutrients. I mean, we, as in the water authorities, measure nutrients to meet to compare against various guidelines, whether they be ANZAC, Australian Drinking Water Guidelines, or other guidelines. And those guidelines help give a sense of, well, are my nutrients a problem or aren't they? But they're very broad. They're designed to capture a whole range of different environments. But they don't really tell you what are the nutrients doing in the system. Let's start with nitrogen and phosphorus, total nitrogen and phosphorus. Now, they're regularly measured forms of nutrients that we measure in water. And I'd argue that they have an important place in long-term trends. They can certainly tell us if we're getting more and more problems with water quality and likely to have more blooms of algae or cyanobacteria. And they can also tell us if our management actions are working, if we're trying to wind back the amount of nutrients that are coming from a catchment. In the long term, are we seeing changes? But it really is about long-term trends. And when I mean long-term, I mean decadal scale trends. However, we have to remember that something like total nitrogen, which gets used a lot in analyses and correlations, but when trying to predict cyanobacterial blooms, total nitrogen consists of ammonia, which is something algae use, nitrate, something algae also use. It's also dissolved organic nitrogen, which is a complex suite of compounds, some of which are bioavailable, some of which are refractory or not used at all. Some of it's in the algae themselves, so you can't actually say that total nitrogen is something algae use. It's in algae, it's used by algae, depending on the proportions. It's in detritus, whether that be bacteria or algae or other things, and it's attached to particles like sediment in the water column. So it's complex, it changes over time, it's an integration of a whole lot of dynamic processes that are going on, and it's very hard to interpret, right? Other than trying to use it, like I say, in long-term trends. The same issues exist for total phosphorus. In that case, it's mostly phosphate that we think about as the most bioavailable form. But there's a whole suite of other types of forms that phosphorus occurs in that will change over time and between different systems and reflects very dynamic processes that are going on underneath. So I'm basically saying I'm not a big fan. Nitrogen to phosphorus ratios. Another area where I have a lot of concerns because they oversimplify the world. Obviously, it's built on the foundation of Redfield's work that's been followed on for a number of years by some other nice papers. And the concept is that within algal cells, we get approximately 16 moles of nitrogen to 1 mole of phosphorus. And that occurs globally. I mean, it's plus or minus a bit, it's fairly consistent. But it only works in terms of understanding how nutrients are used by algae if we have some form of nutrient limitation. If the concentrations are sufficiently high, you know what? an algae doesn't care what the ratios are because there's plenty to go around. And so, but then we don't really know what concentrations are excess and which ones aren't. We know when we do things in culture that they're in excess because we add huge amounts of nutrients. But in the field, we don't really know what are limiting concentrations and what aren't. So it's not just my opinion. There's a lot of papers coming out now saying that using N to P ratios to understand nutrient limitation is a real oversimplification of the world. And at best, it should be complemented with a range of other approaches. The other thing is that it's actually not concentrations that matter if you're an algae, it's rates. And what I mean by that is, imagine you had, for example, for phosphate, you had 10 days supply, right? And you had a bloom. You might argue that, well, that's quite a lot of phosphorus, right, to go around. That's going to keep the bloom going for quite a while. And you might look at a sort of relationship as we see on the right, where the amount of total phosphorus as it goes up, we get more chlorophyll A as a measure of our bloom. It could be cell counts, whatever you want to use. But what about if you only had 1 day's supply of phosphorus there, all right? If you knew how rapidly the cells were using it, you might say, well, that's probably limiting because it's only going to keep the bloom going for another day. It only matters if the supply of phosphorus is exhausted after a day. Just because you measure a certain concentration doesn't mean the rate at which it's being replenished isn't equivalent to the rate at which it's being used. And that is often the case in these systems. So the concentration is irrelevant. It's the supply that's important. And in that case, on the far right, you'll see that you don't get a relationship between the phosphorus that's measured in the water and the chlorophyll A concentration. We've done lots of measurements of rates over the years, and typically the rate of turnover of ammonium nitrate and phosphate is in the order of minutes to hours, right? So that's how rapidly they're getting used and recycled in the system. So going and doing a spot measurement of nitrogen, of nitrate, phosphate or ammonia once a month, in my opinion, doesn't mean anything because it's all very dynamic. And I'm not talking about days or weeks, I'm talking about minutes and hours. Cyanobacteria can change their uptake mode as well. Very clever. And this is well established in the literature, and we've been doing some work on it in recent years in our laboratory and the field. So the classic way we think about nutrients is you add nutrients, and here I've got phosphorus as the example, and the more you get in the system, the more chlorophyll you get. Okay, so they're responding, they're growing, they're taking it up at increasing rates as the amount you add increase, up to some maximum where they physiologically can't do any more. But there's something called active uptake that they have, and that happens at low concentrations of phosphorus. So it seems to be like not all cyanobacteria have been studied, but many have been, and found that active uptake is a strategy they use when phosphate is limiting in the water. And when I mean limiting, I mean down near detection limits, chemical detection limits. So they switch. It's a great strategy because it says, well, running out of phosphorus in the system, I'm going to outcompete other species, and so I'm going to scavenge what's left and I'm going to store it in the cell, right? And so it's energetically more expensive for them to do this, but they do it as a strategy to store what little is left. So they'll only do it when the concentrations are low. And here's a nice example of it from my student, Matt Prentice. What he did was he went out into a reservoir monthly for a year, measured in multiple sites, looked at uptake rates and compared them with their phosphorus, or in his case he's put dissolved inorganic phosphorus concentration. So when we have I will attempt to use this without getting into trouble. All right, so when we have the higher phosphate concentrations, which is typically in the winter months, uptake rates, and this is standardised to chlorophyll A. So it doesn't matter how many algae is there, it's the rate at which they're capable of using the phosphorus. Higher concentrations, we get quite low uptake. When they reach some threshold, and this is about 0.004 milligrams a litre of phosphate, we get active uptake. So they switch their mode and they start this rapid uptake and accumulation of phosphorus. Right. And the interesting thing about that value is that's pretty close to detection limits, right, depending on the lab. And so it's actually quite frustrating doing these experiments because the chemistry methods are really just not actually good enough to keep up with trying to understand the cycling or the physiological processes that are going on. But it tells us that actually that's when they really start to kick in and gain their advantage. Down at concentrations when we measure nutrients, we're often not really thinking are important. We also tend to ignore organic nutrients, and partly this is because there are methodological challenges. Let's look at phosphorus. A nice review by Sonia Diamond, where she looked at, these are all the different forms of phosphorus that are currently known that cyanobacteria can use. Not all cyanobacteria can use them, but they're the ones that are known about. So there's phosphate or orthophosphate, but there's all these other forms as well that can be used. It's really hard to measure them. There's no simple measures for them, and so we tend to ignore them when we measure nutrients in water bodies. Nitrogen's the same, and here's a couple of classic urea and amino acid that are used by algae, and we've done some studies on urea, and algae uptake it just as rapidly as they will nitrate or ammonia, depending on the time and time and place. So really important forms as well, but typically not measured. Urea you can get measured in laboratories, but it's more expensive. So this is, again, when we talk about measuring nutrients, well, we're not actually measuring everything that algae can use, even when we do measure our dissolved inorganic nutrients. And organic carbon, that's an area that people haven't really thought a lot about in terms of, there are a lot of algae out there that can use organic carbon, mixotrophs we call them, and they've been more well studied in marine systems, but not very well studied in freshwater systems. And it's possible that cyanobacteria can use some organic forms as well when they need to. And here's an example of the use of this dissolved organic phosphorus. This is, again, Matt's study where we went in this reservoir and looked, multiple times in places over a year. And he's looked at the internal phosphorus levels within cells, and this is throughout a year, and at this time of year dominated by Cylindrospomopsis, now called Raphidiopsis raciborskii. So when we have these higher internal stores of phosphorus in the cells, then this APA, which is alkaline phosphatase, which is an enzymatic method we use to try and measure the use of organic forms of phosphorus, the esters. When it's higher, we don't get much of that, but beyond some threshold where they start to run out inside the cells, they switch to this mode of using organic phosphorus. So another strategy they use at low concentrations. So it again begs the question, well, if nutrients are in low concentrations and they can switch into different modes of using phosphorus, do we really care what the concentration is, right? Maybe their competitive advantage is not actually in the high concentrations, maybe it's in the low concentrations. I don't know, but it's an interesting thing to think about. All right, so what are some of the ways forward? It's not the nutrients that are the problem, it's the cyanobacteria. And obviously, in addition to being cautious about our use of measuring nutrients, are there other approaches that integrate? Well, obviously there are. We measure chlorophyll, we measure cell counts, we measure dissolved oxygen. They're all things that are measures of an integration of the nutrients that are in the system. But we've been doing some work in recent years about algal growth responses. And I just wanted to give a couple of examples that help complement the use of measuring nutrients to give the nutrients some context. So these are these rapid response bioassays. So what we do, we go out in the field, we collect some water, we put it in bottles, we incubate it at set light and temperature, and then we have a control, and then we have our treatments, which could be nitrogen, phosphorus, nitrogen plus phosphorus, from various places, different forms, etc. And then after 48 hours, typically, we measure it with the phytopan, which is the photosynthetic yield, which is the first step of an algal response, if you like, to photosynthesis, carbon incorporation, growth. So it's a rapid assay, all right? So here's some places where we've used it. So this is some work done by Hannah Franklin as a part of a study that we did with the state government. And essentially, in this case, we were interested in knowing, does soil make algae grow, right? We know that when we get big rainfall events, it's not just dissolved nutrients, there's all these soil particles that become sediment and float around and come downstream. And we wanted to know how much nutrients gets released either chemically or bacterially mediated release of nutrients from that soil. So we collected soil from all these different places, and then we made these slurries. So we artificially created a rainfall event. we put these slurries in dialysis bags, put them in these bottles, and then measured the photosynthetic response. And at the same time, the chemists measured all the things we typically measure in sediment in the water column to see what correlates with the algal response across all these different types of soils. And here's we found a really strong correlation of algal response in terms of nutrient responses to four particular variables: ammonium attached to sediment, phosphate, and this is soil scientist talk, soluble organic carbon and soluble organic nitrogen. So now we have a way of saying which soils are most likely to stimulate algal responses. So it means that in terms of management actions and remediation, you can start to focus on the right kind of soils to give the algal response you want. Another way we can think about it is in terms of nutrient addition thresholds. So back to my question, what concentrations of nutrients are important? You know, that's a really hard one. It depends on your system, right? And so this was studied by a PhD student of mine, Emily Sate, and she actually looked in a marine system. So what she did was she took a transect out from there, sampled multiple times out from the mouth of an estuary, and did these same experiments. But in her case, she used dissolved nutrients and added it to the bottles in a range of concentrations and then looked at the response. And here's what she found. So she's working in micromoles per litre because that's what the marine people do, but I've also given some of the values in milligrams a litre. So this is the concentration of dissolved, it's still there somewhere, dissolved inorganic nitrogen across the x-axis and the response on the y-axis. So when we get a low value, that means that they've already got plenty of nutrients. You add more, they don't respond. If you get a high response, it means add nutrients, they respond. The important thing in this is the threshold. So we start to get a response when we add nutrients at a concentration of 0.028 milligrams a litre of nitrogen, which is a really pretty low concentration. That's the point at which they are replete, right? So if you're thinking about measuring concentrations of nitrogen, in this case, this was ammonium that was added in the field, that's a pretty low concentration at which photosynthesis is happening at a maximum rate. Again, pointing to the challenge of measuring dissolved nutrients and what they actually mean. And a tool that we've used in a range of places, that value changes depending on the environment you're in. We've used that tool in a range of places to try and help us understand what concentration of nutrients matter in my system. All right, so what's the way forward? Well, I've flagged at the start that I'm not totally opposed to measuring dissolved nutrient concentrations or total nutrients because they have a role, but measuring and interpreting nutrient concentrations is complicated. I hope I've shown that, not to show how complicated my life is, but to help you, to provide some context for you in terms of thinking about your nutrient concentrations. And I think there's scope to replace or complement some of these nutrient measures with measures that more effectively integrate the response. Thank you very much.
Okay, we've got time for one or two questions again. Okay, what's one here and then here?
The usual culprits.
Yes,
Yes, the usual culprits. I'm not entirely persuaded that response is the be-all and end-all. Surely there's a combination of factors that have to be considered. You get a higher response at, let's say, low DIP levels, say below 4 micrograms per liter. Now, if you started with a system that only had 4 micrograms per liter and nothing in it, you'll get a high response, and people could think, oh dear, I'm going to have a high response. But the maximum biomass that could be supported by the 4 micrograms per liter is too small to be a problem. So there's got to be a balance between the carrying capacity, which will be set by a mass of phosphorus quite often, and the rate at which you hit that lid in terms of the peak biomass.
But remember what I was talking about with the rates. It depends on how the rate at which the phosphorus is being supplied. So if you've got sediment regeneration or you've got some regeneration within the water column that's occurring rapidly, then the concentration can give you a false impression about the availability in terms of forming a higher biomass bloom.
Sure. I don't disagree with that, but I can show you data from 4 nice data sets that show that the biomass does peak out and that the total phosphorus doesn't increase. And what you're saying implicitly, implies that TP would increase over time in a system, and quite often it doesn't do that. So that's just something to bear in mind in analyzing these things. And I don't think that time has come to completely give up on sampling for nutrients.
And I'm being a bit controversial about it, but I agree they have a role. I just think their role is overstated, or we oversimplify what's going on when we measure the concentrations.
Okay, question from Nick.
Just a comment, really. So in my view, the TNTP is used to describe large spatial trends or long-term trends.
Yep.
It tells you about the eutrophication that's underway.
Yep.
It really doesn't have much bearing on whether you're going to have a bloom this summer or the extent of the bloom. It tells you about if you're going to have more blooms or if they're going to be more aggressive blooms, because you're talking about the total available nutrients, which will eventually be remineralised within the system, right?
Yep.
Which is in contrast, and you're making this point, you just didn't say it, is what's really important from the point of view of a specific bloom is the relationship between nutrients and growth rates.
Yes.
And what is a frequent, trap for newcomers is that people talk about Liebherr limitation, which is probably quite rare in nature. So this is where the standing stock is limited by nutrients. That's pretty rare, actually, in nature, because what happens in nature is nature doesn't normally run to completion like it does in a lab. And that's where Redfield kicks in. But what happens in nature is that, blooms senesce for various reasons. You never reach that ceiling. So you can have a standing stock which is limited by one nutrient, but actually the active growth rate is limited by another nutrient.
Yep.
2 completely different things.
Yep. Yeah, reflecting the dynamism. I just say one point about the total nutrients. I agree what you say about trends. You will be amazed how many papers I get to review where people do correlations using TN and TP with measures of algal response. And it's like, I don't know why you're doing it. Just because you can, I guess. But, so that's the stuff I get concerned about. Yeah, thanks.